this is a problem, we need to think about, yes, carbonyl is a good electrophile, so it can get reactivated. But there's a different type of carbonyl containing molecule depending on what they have substituted. So like here, we got the carbonyl with the 2 hydrogen, that's a smallest aldehyde with the formaldehyde. There's a 1 alkyl chain, that's regular aldehyde. This is the ketones. So how do you figure out which carbonyl is going to be more reactive? And then what is the factor governing that? So that is what I'd like to tell you about using this slide. So what you need to think about it, reactivity to carbonyl. This oxygen is a big electronegative atom, right? That's the one that pick electron density from the carbon of the carbonyl. That's the one that makes electron deficient. The more electron deficient, it can get attacked better, right? So that's the concept. The more electron deficient, it will be attacked better with the nucleophile. Then among these 3, which carbonyl is going to be more electron deficient, which carbonyl is going to be least electron deficient? So that's the things you need to think about. And the difference between all this is that this is a hydrogen and that's the carbon chain. So what we've been talking about is a carbon chain, is an electron donating groups, right? You got electron deficient carbon of the carbonyl, but when you have electron donating groups, shipping electron density to that through the inductive effect, electron deficiency is going to go down, right? The more carbon chain you have. So electronic region, among these 3, which one's going to be the most electron deficient carbonyl? The one has the least number of carbon chain. That will be this one, right? So that will be no carbon chain there. So there's no inductive effect we can expect. Aldehyde, you get 1 carbon chain, so it's going to give a little bit of density through the bond. So this electron deficiency is going to be lower than what you see with formaldehyde. But in the case of ketone, when you got 2 carbon chain shipping the electron density through the bonds, then that's definitely going to be least charge separations. So that is the factors that you need to think about for talking about electron deficiency of the carbonyl for the attack with the nucleophile. So more electron deficient carbonyl, nucleophile can go attack better. So in that case, formaldehyde is the best, then the aldehyde, then the ketone. But there's another factor. As soon as you think about nucleophile attacking the electrophiles, something that you need to think about is static hindrance. Carbon chain has a volume. Hydrogen is much smaller. So if you got the big carbon chain surrounding the carbonyl, it can provide some amount of the static hindrance compared to the ones they have just 1 or none. So to think about that, these are the ketones are going to be probably having a more static hindrance. I mean, still they can be attacked because of the carbonyl is sp2 hybridized. It makes it flat. So it's not like a torsion alkyl that never get attacked by the nucleophile. This is not like that. Still, there's room for the making nucleophilic attack there, but these are 2 chains. It's definitely get in the way a little bit. So the static hindrance is higher with the ketones, and then of course aldehyde, you got a much more open spaces here, but for formaldehyde, you got no static hindrance at all. So those are 2 factors basically determining the nucleophilicity. So aldehyde, formaldehyde is the most reactive, then the aldehyde, then ketones. But even the ketone, depending on what alkyl chain you have, you expect different amount of static hindrance, different amount of electron deficiency. Let's say you got T-butyl groups that substitute both sides of the carbonyl. T-butyl, we've been talking about pretty huge in space. You got 2 of them around the carbonyl, and the nucleophile making a attack to this carbonyl is going to be really difficult because we just size it so much. So now, I mean, of course, the T-butyls are also the good electron donating groups. You got the least amount of electron deficiency there, also very big state hindrance there. So the Berkey carbonyl of the ketones, like carbonyl of the Berkey ketones, is going to be probably not a good substrate for this type of nucleophilic attack. But the small one like this is going to be really great because there's you got the biggest amount of electron deficiency there, and also there's no state hindrance. But you can even make anything better than that. This carbon chain is electron donating groups, right? What will increase the reactivity further is electron withdrawing groups, right? So if you have any of these things have electron withdrawing groups on it, especially substituted on this side, then that will definitely increase the reactivity of the carbonyl more than formaldehyde. So that's how you kind of fine-tune the reactivity using the substituents, natural substituents, either donating or withdrawing. So these are the concepts that you can think about for the ranking questions of the reactivity of the carbonyl. Right? So that is something that I'm going to talk before we move on, because we're not going to just talk about these. We need to talk about something else as well. So how we can use that concept for the making question is something like this. You see here, we have a green methyl magnesium bromide, but just one equivalent. We got 1 to 1. And you are looking at the molecule that's going to react with the methyl magnesium bromide, but it has 2 carbonyls. So they're not going to be, not both of the carbonyls going to get reacted with the methyl magnesium bromide because we added just 1 to 1 ratio. So only one available to whole thing. So the question is, which of these carbonyl is going to get reacted? And how are you going to figure it out? Right. So for that question, you need to think about the most reactive carbonyl probably is going to be the one that get attacked first. And then which was the most reactive carbonyl? Then you need to think about these factors. For the electronic reason, the carbonyl with the least number of the carbon chain will be the most electron efficient. So this is a carbonyl of the ketone with the 2 carbon substituents. This is a carbonyl of an aldehyde. So is the aldehyde more reactive or the ketones are more reactive? And we just talked about that, and then you know the aldehydes are more reactive than ketones. So if the carbonyl, the green is here, you have 2 carbonyl present. We expect the more reactive carbonyl than aldehyde is going to go for the reaction first. If you have an additional methyl magnesium bromide, and then this one attack first, and then second one's going to attack that. So both can be reactive, but if you only adding just 1 to 1 ratio, then only one of the carbonyl need to get reacted. I would say predominantly the aldehyde is going to be the one consumed first because of it has a high reactivity.